Hello everyone, you're welcome to my project presentation. The topic of my presentation is high triple A financial fraud detection with neural networks. Uh, the reason why we have IEEE is because this project is a competition supported by international Institute of Electronics and Electrical Engineers and Cargo. And so the aim of the project is to actually uh, classify a transaction as either fraudulent or not fraudulent. So in my own case, I'll be making use of neural networks to be able to do these classifications because there are various approach, various machine learning or approach of solving a uh, binary classification problem or a logistic classification problem. So in this presentation I will be discussing the problem statement, the data set in the background, how I prepared my data, the model architecture, talks about the parameters and the methods or technique. I'll discuss the experimental result, evaluation metric conclusion, and future work. So my problem statement is to predict the probability that an online transaction is fraudulent. So given a set of features that make up a particular transaction, we want to classify that transaction as either fraudulent or not fraudulent. And why is this problem so important? Millions of dollars are being lost per year by consumers as a result of fraud in online transactions. And so we're developing a model to be able to improve the accuracy of our detection system to be able to spot fraudulent transactions. At the same time, we're also careful to make sure that our system is uh, being fair to customers to use. We don't want our system to be having false positives. That will be very inconvenient to customers. We want our system to be precise enough to actually be able to catch, forge, and at the same time allow uh, authenticate legitimate transactions to go through. So in this problem, uh, and the target variable that represent whether a transaction is fraud or not is tagged is fraud, is named is fraud. Our data set. This is an histogram showing the class distribution of our data set. As it is for every machine learning problem, every deep learning project, we want to have a feel of what the distribution of our data set is so that we can understand the intrinsic problem in the data set. For instance, considering this data set, we have definitely a skewed data set. A traditional machine learning approach or model that classify all transactions as class 0, in which case class 0 is no fraud. That means there are no fraudulent transactions. we have a very high accuracy because the number of transactions that are actually fraud are very minimal. But we want to develop a model that will be able to accurately classify transactions that are class 1, that is, that are fraudulent, and differentiate them from transactions that are class 0, that are not fraudulent. So this is an example of the transaction. You will see the column is fraud. Majority of them are zeros, meaning no fraud. Now, according to Vesta Corporation, they reported, because this is a problem on cargo competition, she reported that how they labeled the data set, that a data instance, a transaction in which they have a reported charge back either on the card or user account, any transaction of such will be classified as a fraud, which is class 1. But if any of this does not happen, then after 120 days, then they classify the transaction as legitimate. This is to show us that the corporation is very interested in transactions that are fraudulent. So they assume, as it were, that once there's a chargeback, then the transaction is fraudulent until after a number of days. 1. How did we prepare our data? The data set provided by Cargo is in 2 files. We have the train transaction.csv and the train underscore identity.csv. Each of these CSV files has separate number of features, or what you also know as attribute. And there is a common features between these 2 files, and that is transaction ID. Then the choice comes into how do we match these 2 files together? Do we do an inner join on the common feature, which is transaction ID? That is, we pick those that are common to the 2 CSV files. Do we pick all the records in which we have a matching transaction ID on the 2 CSV files? Or do we do a left outer join or a right outer join in which we take all the transactions from one file irrespective of whether it exists on the other file? But in our own case, we decided to do a full outer join. That is, combine all the transactions on the train transaction and all the transactions on the identity, and we just match them all together. This, as a result, is going to leave a number of columns or a number of features as none, as empty, as not having an attribute. So another problem is, by the time we inspect the data, there are some transactions, some instances, data instances that do not have values, that their values are missing. So in this project, we decided to drop all the rows if all the feature values are missing. Some of them in which we have a non-object types, where we have like numbers, the non-object are replaced with their mean values, calculated the mean and replaced with mean values. The object types, those are like emails, like email addresses, like street addresses, are converted into a categorical data and one out encoded. Then we mean normalized with standard deviation. As if we subtract each training data from the mean and divided by the standard deviation. That is performing feature normalization. This is the model architecture I used. You will see that this model architecture is a very simple model architecture. I have 432 input unit and just one neuron in my output layer. So this is just a one layer neural network. Someone will say, why a one layer neural network? Why not something deeper? That is to show the ability of neural networks that as simple as this one layer neural network is, it performs really very well. So the learning rate that I used, I experimented with a number of learning rate. The learning rate that gave me appreciable best result is 0.03. The optimizer uses SGD. The loss function is binary cross entropy. The activation function is sigmoid. The number of epochs is 10. Total number of parameters in my network is 433. You have 432 input plus one bias, making 433. Now, another technique that was used to be able to undo the class imbalance problem because of the skewness of the data, I decided to use smooth to create new synthetic observations. Before smooth, we have approximately like 590,000 samples, and after smooth, we have like 798,000 samples, which means the number of synthetically generated data points is close to like 200,000. Now, this is a decision that had to be made because there are other ways of addressing class imbalance problem. We could have also used random undersampling and some other advanced sampling techniques, but I decided to go with smooth because in many literatures, random oversampling has proven to work well. Experimental result. Now this is a plot that shows my training and validation accuracy and loss. You see here that we have our training accuracy is pretty very high compared to the validation accuracy, and you will see that the loss on the training is getting smaller and smaller. It's pretty very low, but the loss on the validation, it's very high, so the gap is a little bit wide. Anyone could quickly spot that this model is definitely overfitting, and that's something I'll come back to in few slides. So this is the model, this is the performance of the model, and this graph shows the model training and validation. On running this model on Kaggle test set, this model scored 86.31% on the public leaderboard and 83.73% on the private leaderboard. During the competition, Kaggle releases scores for the public leaderboard, which is 86.31%. At the end of the competition, Kaggle releases the private leaderboard, which is 83.73%. The public is calculated on 20% of the test data set from Kaggle, while the private is calculated on 80% of the data set. You could see that our model has not done so badly. Now the question is, this model is overfitting, but yet it has given appreciable good result. So it calls for a question that can overfitting be a good thing? It's a question that demands an answer. Could there be some circumstances? Could there be some set of problem or data set that overfitting could be a good thing? Wow. This experimental result, the model puts me on the top 85% in the competition. This is the hardware used, Intel CPU 3.3. The memory is around 26 gig thanks to Google Collaboratory. The evaluation metrics is accuracy. We try to measure how many instances data model got correct compared to all the available data set. Now, trying to look at some baselines and make comparison. The team that actually came first in the public leaderboard, the team was number second, and they had the highest the score of 0.9677. That is during the competition. At the end of the competition, the team had a score of 94.588. If you check this, you will see that the score of 96.77 on public leaderboard and 94.58 on private leaderboard is also a representative of the score of my model that I submitted of 86.31% and 83.73%. This also reinforces that this model is not doing badly at all. If you still further inspect at other, like the team Two Uncles and Three Purples, a similar thing that you will see both on the public board and on the private leaderboard, and also other top performing teams. This further reinforces my question of, could my overfitted model actually be a good thing? Some of the background works, literatures are these. Machine learning are going to tend to be overwhelmed when you have majority skewed class distribution. There are various ways of which you can address class imbalance. Some other works in which supervised and unsupervised learning has been done. In conclusion, in this work I have competed on Kaggle to develop a model to detect online fraudulent transactions. On Kaggle private leaderboard, the model was able to perform very well and even moved up 52 participants from the public leaderboard to compare to when the private leaderboard was. So it even did better in the 80% compared to the 20% of the data set. And we're ranked top 85% out of 6,000 participants. Future work, I would like to know why overfitting gives a good performance on the test set. I'd like to investigate that. I'd like to try out random undersampling. I'd like to try other methods of handling missing values. Try out inner join and see what that gives. These are references. Thank you for listening. Crucial.